Take a look back at your stair lab. When we did this lab, we calculated the amount of work that was done when you walked up the stairs and the amount of work that you did when you ran up the stairs. Since work is a change in energy, and the energy that changed was the gravitational potential energy, the work done in both situations was the same. So if you did the same amount of work, whether you ran or walked, why would you feel more tired after you ran? The answer really lies in how fast you did the work. Your rate of work was faster when you ran than when you walked. A rate is simply how fast you do something. So while the change in energy was the same, the time it took you to expend that energy was not the same. When we talk about the rate of work being done, we define that as power. So power is the amount of work done divided by the time it takes to do it. Since work is measured in joules and time is measured in seconds, the label for power is joules per second. And we give this its own unit of watts. Now I want you to pay close attention to the letters here. P in our equation is power. W in the equation is work, and that's measured in joules. The T in the equation is time. Notice now that we are going to label our answer with another W. The label W is watts. The variable W is work. Refer back to your data from the stair lab. Use the work that you did to climb the stairs and average time you measured in each trial to determine your power output for when you walked up the stairs and your power output for when you ran up the stairs. So say two people climbed to the roof of a building. The older gentleman walked up a gentle ramp. The younger man climbed up a steep spiral staircase. Which person did more work? Remember, we are moving in a vertical direction, so the change in energy involves the change in height. Assuming the two men have the same mass, we would say that since they both ended up on top of the same building, they would have both done the same amount of work. Say you do work when you shovel your driveway. If you use a snowblower, is the work done more, less, or the same as when you shovel it? So we are going to have to apply the same amount of force to the snow over the same distance, whether we apply it with a shovel or with a snowblower. So the amount of work done will be the same. Now what about power? When shoveling versus using a snowblower, is power more, less, or the same? The snowblower will probably be able to move the snow much faster than the shovel. So the power output of the snowblower will be more than the shovel, even though they do the same amount of work. Say we have a 60-kilogram box that is lifted by a rope a distance of 10 meters straight up at a constant speed. How much power is required to complete this task in 5 seconds? So we know the mass of the box, the distance that we lift it, and the time it takes to lift it. We also know that to find power, we need to take the amount of work divided by the time. So we know the time, but we don't know the work. But can we find the work? Yes, we can. We know that work is a change in energy, and since we are lifting the box, the energy change will be in the vertical direction. This means we have a change in gravitational potential energy. So to find the amount of work done, we are going to take the mass times the height times g. We have all of that information, so that gives us 6,000 joules of work done. Now we can go back to that power equation and use the 6,000 joules as the work and divide that by the 5 seconds it takes to lift the box. And we end up with 1,200 watts of energy. Lover's Leap is a 122-meter vertical climb. The record time of 4 minutes and 25 seconds was achieved by Dan Osman, who has a mass of 65 kilograms. What was his average power output during the climb? This is a similar problem to the last one in that we are given the mass, the height the guy climbs, and the time it takes him to do it. Power is still equal to work over time, and we again do not know the amount of work done. But we can find it. This is a change in gravitational potential energy, so mass times g times height gives us 79,300 joules of work done. So power is going to be this work divided by time. But the tricky thing here is that time is given in minutes and seconds instead of just seconds. So we need to convert that into just seconds. Every minute has 60 seconds, and there are 4 of them. So that's 240 seconds, plus another 25 seconds is going to give us 265 seconds to make the climb. Now we can plug in the work and the time to find that 299 watts of power was generated. Now, another way we can look at power is in terms of force and velocity. Power is the work divided by time, and we have also defined work as the force times the distance. Physics loves to combine equations, and we can combine these two together by putting the force times distance in for work in our power equation. And then something really cool happens. In our new equation, we have distance divided by time. Remember way back when we talked about velocity? We defined it as the distance divided by the time. So we can rewrite our equation to say that power is equal to the force being exerted by our object times its velocity. Take a 1994 Ford Mustang that is driving down a road with a constant speed of 30 meters per second. The engine must exert a 5,000 Newton of force to maintain this speed. What is the power rating of the engine? Well, we know that the force exerted by the engine, and we know the velocity of the car. So this is a pretty straightforward question, where we plug in the force and the velocity to find 150,000 watts of power generated. So what does this mean in terms of power? What can we relate this to? You've probably heard of engine power referred to in terms of horsepower. 1 horsepower is equal to 746 watts. To convert the watts of our engine into horsepower, we take the 150,000 watts and divide it by 746. And this translates into a horsepower of 201.